Hello guys, welcome to this tutorial number 5, basically under momentum. So I'm just going to run you through on how to solve the questions. So of course you're going to have to solve like on your own, get a piece of paper, go through, okay, for practice. So I'm doing this because if I use Google Meet or Zoom, sometimes some of you never log in. Others do, but then there are just few. So at least if I just send the video, you can always access it whenever you come online. Okay. So let's start here with question 1. Question 1. It's just a conceptual question here. If you remember the other tutorial sheet on motion, talking about a baby falling from the bed, so it's similar to this one. So we are being told that the boxers in the 19th century used their bare fists. In modern boxing, fighters wear padded gloves. So how do gloves protect the brain of the boxer from injury? Okay, so again, you remember the carpet floor and the wooden floor? Yeah, this question is similar to that. Okay, so here, of course, you may have some better answers, but so what we need to know is if you strike the head with your bare fist, you know the head accelerates rapidly because the impact force which is applied there is applied over a very small amount of time. So meaning that the impulse actually is much greater, and this causes a larger acceleration. And we know that when the brain is accelerated at very high rates, it causes injury. Okay. So that's what it's just basically saying there. Then padded gloves, we have, those are soft, so they act like a cushion. When you hit someone with that, at least they extend the time over which the force acts. Okay, so we know that the force, it's F. Okay, so let me not do this. We know that F equals change in momentum over the time. So if the time is increased, then it means the force is reduced. And if the force is reduced, then the acceleration is also lessened. Therefore, the gloves are going to help prevent, or rather reduce the chances of the injury. Okay, so yeah, that's that. We go to question 2. Question 2, I reserved it as your assignment. Go and answer it. It's very easy. I just picked this one. Yeah, it's basically 3 marks, so but at least write something sensible though. Don't just write 2 sentences and then you're done. No, I expect something sensible. So I'll attach an email as I send this video to you so that you can send me the assignments. You scan them, make them PDFs. Okay, so over to question 3 here. Question 3, we have 2 cars, one at rest, the other one moving with an initial speed. Okay, so both these cars have identical mass. Okay, so M1 is equal to M2, which is simply M. Okay, so now we are told that the second car was at rest and the first car came to actually hit the second car from the rear. Okay, and after this happens, they both skid for a distance of about 6 meters in the original direction of motion. Okay, so one thing I need to mention here is that in an elastic collision, both momentum and energy are conserved. Okay, so the question further says, if the stopping force is about mu times the combined weight of the cars, okay, meaning that mu times 2m, okay, because we have two masses that are equal, so instead of just m, it's going to be 2m. So we have we have mu times 2m as the stopping force. We have to find now the approximate speed of the second car just before the collision. Okay, so the car which was coming to hit the other one, we need to find the initial speed of this car. Okay, so yeah, that's my rough sketch. May look like this. So car 1 at rest, car 2 comes to hit this one, and they skid together. As they skid together, notice that the final speed is the same for both. Okay, they're going to skid with the same speed, and their mass will be combined as 2m. Okay, so now we know that they are skidding. Okay, and if they are skidding, then we are talking about friction here, since their brakes are applied. So it means whatever change in energy that is going to take place there, it's going to be equal to the work done by friction. Okay, so in this case, the energy that we have is the kinetic energy. So the change in this kinetic energy will be equal to the work done by the friction force. Okay, where the work done by friction is simply the energy change, kinetic energy change equals work done by friction. Yeah, like that. So where the work done by friction is the same as the normal force multiplied by the distance. Normal force multiplied by the distance. Okay, and we know that the normal force Fn is equal to mu mg. Okay, is equal to mu mg. But here, remember that our m in this case is 2m because we are dealing with two masses. Okay, so then we have that half mv squared equals mu mg times the distance. Okay, remember again, but m is equal to 2m. Therefore, if we substitute in the change of energy, we are going to have half 2mv squared equals mu 2mg times the distance. Okay, I hope this makes sense. So if you work that out, you're going to realize that the mass is going to cancel out. Okay, the mass is going to cancel out, and you're going to remain with v squared equals 2 mu g times the distance, and you get that, and then you proceed, find v as v equals square root of 2 mu gd, and then finally you can simply evaluate, and then you find your final speed for both cars as 9.07 meters per second. Okay, so now we know that as the cars are skidding, they are moving with the speed of 9.07 meters per second. Okay, but what we want to find here is the initial speed of the second car. Since we know that the first car was at rest, so the initial speed of the first car is 0. Okay, so now we have dealt with the energy conservation. Let us now see the conservation of momentum. Okay, so what does the conservation of momentum give us? We have two cars, and it's saying that the total momentum before the collision must equal the total momentum after the collision. Okay, so now we have mass 1 and mass 2, and the total momentum before the collision is simply m1 u1 plus m2u2 equals the final, which is m1 v1 plus m2 v2. But we know that the first vehicle is at rest. Okay, we know that the first vehicle is at rest, meaning that u1 is equal to 0. Okay, and also that v1, which is the final speed of the first vehicle, and v2, the final speed of the second vehicle, are equal. They are v. Okay, the v that we just found here, this is our v, the 9.07. Therefore, we are saying that v1 is equal to v2, which is v. All right, so after substituting that u1 equals 0, there we are getting m2u2 equals m1v, okay, plus m2v. So instead of v1, v2, we are just putting v because we are saying v1 and v2 are just equal and they are equal to v. Okay, so also notice that mass 1 is the same as mass 2, which can simply be regarded as m. All right, so if we do this and put back in our equation, we are going to get mu2 equals mv plus mv, okay, from which we are going to get u2 equals 2v. All right, so if we do this, we know what v is, and it can be easy to find u2 now, which is the initial speed of the second car. So we now say that u2 equals 2 times v, giving us 18.14 meters per second. So this is the initial speed of the second car. Okay, so that was easy there. Okay, so you can always try to solve this on your own. If you are a bit behind, that's why it's a video, you can always take it back. Okay, yeah, so let's see question 4. So question 4, we have this setup here. Okay, we have this bullet hitting the block, and after hitting the block, this bullet emerges on the other side, of course, with some final speed. Okay, so the block as well, after being hit by the bullet, it's going to move in the direction of the bullet, except that this time it's attached to a string, so it can't follow the same direction of the bullet, but instead, because of the string attached, it will simply rise to some height. Okay, so as it rises to this height, it's going to gain some potential energy. Okay, so as it moves from rest here, it's going to gain kinetic energy, which is later converted to potential energy. Okay, so energy is conserved here. Momentum also just has to be conserved. Okay, so in the question here, we have a bullet of mass 10 grams traveling at that speed, strikes a block of mass 2 kgs suspended by a string of length 5 meters. The bullet goes through the block in a very short time, and the center of gravity of the block is found to rise a vertical distance of 10 centimeters. Okay, so they want us to find the final speed of the bullet after it emerges from the block. Okay, so let us consider the conservation of momentum here. Okay, so we are saying that momentum before should equal momentum after. Okay, conservation of momentum. So if we consider the bullet to be our M1 and the block to be our M2 here, this is our bullet, that is our block, and then we can write the conservation of momentum as momentum of the bullet plus momentum of the block these are initials, equals final momentum of the bullet plus final momentum of the block. Okay, so we know that the block is at rest initially. Okay, so U2 is going to be 0. Oh, excuse me. So U2 is going to be 0, and if U2 is going to be 0, then we know that the initial momentum of the block is also a 0. Therefore, we remain with M1 U1 equals M1 V1 plus M2 V2. Okay, so we actually have the values of U1, M1 as well as M2, these values here. We can always substitute them, and then makes the equation look more simpler. So if we substitute, we have that, we're getting that, and then finally we have this. Okay, so the conservation of momentum has given us equation 1. Okay, so we have equation 1 there resulting from the conservation of momentum. So now let us see the conservation of energy. Okay, what are we getting? From the conservation of energy, we are being told that the block loses some kinetic energy, which is converted to potential energy. Okay, so we are saying change in kinetic energy of the block equals its gain in potential energy. Okay, so of course here we are going to use its final because the initial is 0, so there's no need of indicating that. We know that the kinetic energy of the block is half M2 V2 squared, which is equal to M2 GH. Okay, so we know that M2 is 2, which is in gray here. That 2 is going to cancel out with the other half, and then we're going to remain with V2 squared equals 2 times G times H, and we have our V2 squared as 1.96. Okay, giving us V2 as 1.4 meters per second. Okay, so now we remember equation 1. Equation 1 here. We can find V1 now. Since we have found V2 as 1.4, we simply substitute the value of V2 into this equation 1 and solve for V1. Okay, so if we do that, we are going to have 5 equals 0.01 V1 plus 2 times 1.4, where 1.4 is our V2. Therefore, we have V1 equals this guy over here, giving us 220 meters per second. Okay, so this is the final speed of the bullet as it emerges from the block. Okay, all right, so just hope you're following through. Yeah, so you can actually try these on your own. They're quite easy. Okay, so question 5. Question 5, 23 grams bullet traveling at 230 meters per second penetrates a 2 kg block of wood and emerges cleanly at 170 meters per second. If the block is stationary on a frictionless surface when hit, how far does it move after the bullet emerges? Okay, so this question here, it's not supposed to be how far, but it's supposed to be how fast. Okay, how fast does it move after the bullet emerges? So meaning that we have to find the final speed of the block. Okay, we're just finding the final speed of the block after the bullet has emerged from it. Okay, so now the rough sketch here. This is my sketch. We have this bullet as U small letter B, that is the initial speed of the bullet, and we have U capital letter B as the initial speed of the block. Okay, so we know that the block is at rest, meaning that U capital B is 0, and the initial momentum of the block is going to be 0. Okay, So now that we have the final speed of the bullet after passing through the block, the only thing missing from this equation is going to be V capital B, which is the final speed of the block. Okay, so the conservation of momentum is saying momentum before must equal momentum after. Okay, so here this is what we have. Momentum before must equal momentum after. Okay, and we know that UB is 0, therefore the momentum, this guy here, becomes 0. So now we are going to remain with MB UB, where small b stands for the bullet. So we have the initial momentum of the bullet being equal to final momentum of the bullet plus final momentum of the block. We have these values. We are looking for V capital B here. You can simply express VB in terms of U small b, M small b, V small b, as well as M capital B. And it's giving you VB as this. Okay, so when we substitute the values in there, we're going to come up with that. Okay, and then finally we have the final speed of the block as 0.69 meters per second. Okay, so here we are actually given everything except for the final speed of the block. So this one, yeah, it was quite easy actually. Don't expect any trouble on this. Okay, so that's all on this question. That was question 5. So now we go to question 6. So question 6 here, you remember the one for 2 cars skidding together. Yeah, so this one is a bit similar to that. So we have a skater here moving at an initial speed of 10 meters per second. Then he crashes into his friend or her friend of equal mass. Okay, so after the collision, these two move as a unit, okay, together. They move together with a final speed of 5 meters per second. Okay, so if the average force a skater can experience without breaking a bone is 4,500 newtons, and if the impact time is 0.100 seconds, does the bone break? Okay, so here they just want us to find the force, the impact force on each skater as they hit each other. Okay, they want us to find the impact force on each skater, and then we compare that to the threshold of breaking a bone, which is 4,500 newtons. Okay, so here we know how to find the force. We know that the force is equal to the change in momentum over the impact time. Okay, change in momentum over the impact time. So we are going to look at the change in momentum for skater number 1, okay, over the time, which is the impact time, as well as the change in momentum of skater number 2 over the impact time. So we are finding the impact force on skater 1 and skater 2, or M1 and M2. So I'd rather use M1 and M2 here. So let us begin with M1. We know that the force on M1 is going to be the change in momentum of M1 divided by the impact time, which is here we have change in momentum over the impact time, which gives us P final minus P initial And then we know that the mass of this M1 is 75 kgs, and the initial, or I mean the final speed here is 5 meters per second. Okay, so the initial for the M1 was given as 10 meters per second, so we simply say F1 equals final momentum minus initial momentum over t, which is equal to that over our t. Okay, simply substituting the values here, nothing very tricky. So if we multiply and subtract there on top, we're going to have minus 375 over 0.1, giving us a force of minus 3,750 newtons. Okay, so this is the impact force on M1. Okay, so the first skater experiences a force of negative 3,750 newtons. Okay, so what about M2? How much force does M2 experience? So similarly, we're going to say change in momentum for for M2 being equal to that, P final minus P initial, and it's going to give us this, the force on M2 equals the final momentum minus initial momentum over T, and then we're going to substitute the values of M2, V2, M2, U2, and we're getting this over the time. Okay, we multiply and subtract and divide by 0.1. We're going to get this guy, which is going to give us a positive 3,750 newtons. Okay, so the threshold, we know that is 4,500, and both M1 and M2 are experiencing a force of 3,750, which is equal in magnitude, though different in direction. Okay, so then if we consider their magnitudes still more, we find that F1 and F2 are much less than the threshold. Okay, so because they are much less, we are going to discover that no bond is going to break. Okay, so no one or none of them is going to break a bond. They are going to go just fine. All right. Okay, so yes, that's what we are supposed to find here, just the impact force on each skater, and we have found. After finding that, we compare to the threshold for breaking a bond, and we have discovered that the forces are actually less, so no one is breaking a bond. Everyone is okay. Okay. Question 7. Oh, this one. Okay, question 7. Question 7. Well, the data is there, everything is there. You have the question, you have those diagrams. So let's go straight. We have this setup here. Okay, so we have block 1, so to say. We have block 1. I'm going to name this guy as 1 and the smaller one as 2. So this one, block 1 slides on this surface and then meets block 2, hits block 2, and they both fly as projectile like that. They go in that direction. Okay, so notice here energy change, or rather energy conservation, as well as conservation of momentum. Okay, so block 1, if we take a look at this, is going to lose some potential energy, because from the top there to the table where block 2 is, the height is about 0.3 meters. So for him to come from that top there to the table is going to lose some potential energy. Okay, but notice that as the block loses the potential energy, it's gaining kinetic energy because it's moving. Okay, so when this block 1 comes to reach block 2 here, we are going to start on a new a trajectory here as they fall together. Okay, so that velocity that block 1 is coming to hit block 2 with is going to be the initial velocity for this motion here. Okay, so therefore the speed that block 1 will attain as it slides from the top there is going to be the initial speed. Okay, so now as the blocks start falling as projectiles here, we are going to have to calculate the time of flight first. Okay, how long it took for them to fall a height of 0.9 meters, and after finding the time of flight, we are going now to find the horizontal distance for each from their final velocities. Okay, notice here that the only velocity they have now is the x velocity because they don't have an initial y velocity here. Okay, so let's go through the working. We have that the change in potential energy of block 1 is equal to its gain in kinetic energy. Okay, so we have m1 gh being equal to half m1 u1 squared. The masses are going to cancel out. We remain with u1 squared equals that, and then okay, so we now know the initial speed of block 1. Okay, the larger block. So this is the initial speed with which it moves as it hits the smaller block. Okay, so now let's see the conservation of momentum. Momentum before equals momentum after, and we have this m1 u1. We know what u1 is, m2 u2, but again we are told that m2 is simply half of m1. Okay, so we have this, but m2 is equal to m1 over 2 and u2 is 0. We substitute these guys here. We are going to have m1 u1 equals m1 v1 plus 0.5 m1 v2. Okay, so we factor out the m1. We are going to remain with this guy here, and if the m1 disappears, we are going to remain with u1 equals v1 plus 0.5 v2. Or alternatively, we express v1 in terms of u1 as well as v2. We are going to have v1 equals this. So we can call this our equation 1. Okay, from the conservation of momentum. Okay, so conservation of momentum has given us v1 equals u1 minus 0.5 v2. Okay, so from here we now consider the conservation of kinetic energy for the whole system. Okay, conservation of kinetic energy for the whole system. We are saying kinetic energy before should equal kinetic energy after. Therefore, kinetic energy before we have half m1 u1 squared plus 0 because block 2 was at rest, so there's no kinetic energy there, equals the final kinetic energy, which is half m1 v1 squared plus half 0.5 m1. Notice that this is m1 over 2, the 0.5 m1. Okay, because m2 is simply m1 over 2. Okay, that's why there's another 0.5 there times v2 squared. Okay, therefore we factor out the half m1 and we're going to remain with u1 squared equals v1 squared plus 0.5 v2 squared. Okay, so that is what we are remaining with, and we write this clearly, and we're getting that. Okay, so we can call this our equation 2. Okay, so now notice that equation 2 is saying u1 squared equals v1 squared plus 0.5 v2 squared. Okay, so v1 squared, we know that equation 1 gives v1 as this. Okay, so this is our v1 here. This is our v1. So if this is our v1, we are now going to square this so that we can put him here. Okay, we can have v1 squared. Okay, so if we square that v1 squared from equation 1, we are going to get this. Okay, we are going to get this. Do this, try it, work it out, you are going to find it. And okay, simply substitute. So now that we have squared the v1 in equation 1, we are going to substitute this v1 squared into equation 2. Okay, so we are substituting this into here. Okay, that is where v1 squared is. So then we are going to have that we're going to have this u1 squared equals v1 squared plus 0.5 v2 squared. Okay, we work that out, we are going to discover that we can solve for v2. Okay, we can actually solve for v2. We know that we are going to have a 0 being equal to that. Okay, yeah, it's just mathematics here. You can try it. Yeah. So we do that, we keep working. We are going to realize that u1 is going to be 0.75 times v2. Okay, and once you have reached here, you know that u1 was given as 2.42 meters per second. So the only thing remaining here is simply v2, which will be u1 over 0.75. Okay, so this has actually helped us to find v2, which is the final speed of the smaller block. Okay, so we now know the final speed of the smaller block. Let us now find the final speed of the bigger block, which is v1. We know that from equation 1, we have v1 equal to u1 minus 0.5 v2. u1 is given, or rather it is known, minus 0.5 times v2 we just found here. We just found it's there. Simply substitute 3.22 and we get v1 as 0.81 meters per second. So this is the final speed of the bigger block, which is our m1 here. So now we know their final speeds. Okay, so these final speeds we are considering here are the speeds that the blocks travel with along this trajectory here. Okay, so we know that the velocity in the x direction does not change for a projectile. Okay, it is constant. There is no acceleration in the x for a projectile. Okay, so now to find their distances, we use the equation x equals vx times t, where t is the time of flight. So you can see that first of all, we need to find the time of flight, okay, because they are both taking the same time, or rather the same amount of time to reach the ground. Okay, so to find the distance for block 1, we are saying it is going to be x1 equals v1x times the time of flight. So we know that v1x is the same as v1, which we just calculated here. So it's going to be v1 times t. Similarly, for block 2, it's going to be x2 equals v2x times t, which is the same as v2 times t. Okay, so how do we find this time of flight? Since it's a projectile here, it's falling through a height of h, we're going to use this equation of motion as h equals uy times t plus half gt squared. Okay, but we know that uy is 0, so we're simply going to remain with h equals half gt squared. Our h is 0.9 there, so 0.9 equals 4.9 t squared, from which we find our time as 0.43 seconds. Whoosh, this question is long. Okay, so that is our time of flight. Now we can find our x1 and x2, since we already know our v1 as well as our v2. Therefore, the distance covered by block 1, which is x1, equals v1 times the time of flight, which is going to give us 0.81 times 0.43, and then we have 0.35 meters. Okay, so this is the distance that the bigger block is going to cover in the x direction. Okay, then the smaller block, we have x2 equals v2 times t, which is 3.22 times the time, and we're getting 1.4 meters. Okay, which makes sense, because if we look at this setup here, okay, this bigger block is sliding here and it's going to hit the smaller, so the smaller block is going to travel a further distance than the bigger block. Okay, so it is hit and then it's going to fall at a further distance than the bigger block. So x2, the smaller block, is falling 1.4 meters away from the table, whereas the bigger one falls 0.35 meters away from the table. Okay, so we are also done here. I'm also going to attach the PDF of these solutions. You can always use that also for reference. Yeah, here I'm just trying to explain what is going on. Yeah, otherwise, well, nothing is difficult. So okay, so question 8. Okay, so question 8, this guy is crashing. Okay, hits into a wall and then rebounds, bounces. I don't know if it bounces or what, but it rebounds, meaning it hits the wall, and then because the wall is so strong, the car simply bounces back like that. Yeah, well, so now the mass of the car is given, which is 1.5 times 10 to the power 3 kilograms, and is traveling at an initial speed of 15 meters per second. Then after bouncing back, the rebound speed is 2.6 meters per second, and the collision only lasts for about 0.150 seconds. Okay, so now they want us to find the impulse delivered to the car due to the collision, and B, the magnitude and direction of the average force. Alright, so well, this one is very simple here. If we want to find the impulse delivered to the car, we only need the formula for the impulse, which is impulse equals the force times the time of the impact. Okay, impulse equals force times the time. Okay, so we know that force times time in that other formula for momentum change, we know that F equals change in momentum times, divided by time. F equals change in momentum over time. Okay, so meaning that Ft will be the change in momentum. That's all. So therefore, okay, so this is the diagram, how it looks. So in fact, this guy is even going to the left, so you can tell that the velocity is negative initially. Okay, it's heading towards the negative x-axis, and as it bounces back, the rebound speed is 2.6 towards the positive x-axis, so the rebound velocity is positive. Okay, so now let us see. We are saying that the impulse is equal to ft, okay, where ft is simply the change in momentum. Therefore, we can say that the impulse is just the change in momentum, which is simply that. All right, so we can simply substitute, and we are going to get m1 v1 minus u1, and it's giving us, we know the mass, we know the final speed, which is the rebound, positive minus the negative one here. Okay, so that is simply going to add, and we're going to have the impulse as 2.6 4 times 10 to the power 4 kg meters per second. Very simple. Okay, then the second part requires us to find the average force, and we know that F equals change in momentum over time, which is giving us that over t, and we already found the change in momentum somewhere here, which is the impulse, so to speak. So you can notice that this is our change in momentum, which is our impulse. So if we come to this other part here, the change in momentum is simply the impulse over the given time. Okay, so then we can find now the force, which is a positive value, and because it is positive, we know that it's heading towards the positive x-axis, which is to the right. Okay, so the force is positive 1.76 times 10 to the power 5 newtons towards the right. Okay, so we're done. We're done. Naipwa. Okay, question 9. Squids. These questions also. Squids, what's a squid anyway? Yeah, this same squid. We're being told it's the fastest marine invertebrate, using a powerful set of muscles to take in and then eject water in a form of jet propulsion that can propel them to speeds of over 11.5 meters per second. What speed would a stationary, so stationary, we already know something is 0 here. What speed would a stationary 1.5 kg squid achieve by ejecting 0.100 kgs of water at 3.25 meters per second? Okay, so it's like this squid, I don't know if it's a fish or whatever animal it is at rest, okay? But in order for it to move, it has to swallow water and then spit it with so much force that it actually propels itself to some speed, okay? I don't know how I can describe this one, but just try to picture it, something like that. Okay, so then this is what is happening. We're going to consider the change in momentum here. Okay, we have water as well as the squid. Okay, we just say fish, this fish. So we have the fish and water at rest. Okay, nothing is moving. Okay, but when this fish does what it does, it's going to propel itself, okay, to some speed, and it's also at the same time spitting water at some speed. Okay, so you can see that the initial momentum, since they are both stationary here, the initial momentum for both is 0. All right, and the mass of the squid is 1.5, and the final speed of the squid is 11.5. The water, the mass is 0.1, and the final speed of this water which is ejected is 3.25. So things become very easy here. Okay, things become very easy. So now they want us to find the speed of this squid. Okay, let's see. Conservation of momentum before equals momentum after. Mass of squid, so notice here where I have put S, it means the squid. Where I have put W, it means water. Okay, so momentum of the squid, initial momentum of the squid plus initial momentum of the water equals final momentum of the squid plus final momentum of the water. But we know that both are stationary, meaning that the initial momentum is going to be 0 for both. Okay, both S and W are at rest initially, so initial momentum, or rather the total initial momentum, is 0. Therefore we remain with 0 equals final momentum of the squid plus final momentum of the water. Okay, we know the mass of the squid. We don't know the final speed of the squid, but the rest is known. The mass of the water as well as the final speed of the water is given. So 0 equals 1.5 Vs plus 0.100 times 3.25. We can therefore find the final speed of the squid as negative 0.22 meters per second. So why is this negative? First of all, that's why I was saying, trying to picture this. So it's like this guy is spitting water on one end, but then as he does that, the spitting actually propels him to the opposite direction. Okay, so if it was spitting the water to the right, then its motion is going to be towards the left. This is what is happening. So this simply means that the final speed of the squid is in the opposite direction to the final speed of the water. Okay, so it could be, yeah, well, just that. Okay, so we have actually found that. So question 10 again. Oh, this is a long one. So read, you can manage to read, but here what is happening is that where we have a force, an acceleration, as well as a pressure which is responsible for some damage. Okay, so we are being told that if a force is beyond 90 kilonewtons, then your tibia, I'm sure this is some type of bone somewhere, so it's, you can simply say bones in general. Okay, so if a force of 90 kilonewtons is applied to a bone, then that bone is going to fracture. Okay, also we are being told that an acceleration of about 150 g, okay, which is simply 150 times g, where g is 9.8 meters per square second. Okay, so an acceleration of about 150 g can cause death. Remember that thing we looked at acceleration of this much causing brain injury or concussion, yeah, something like that. So it's a similar situation here. An acceleration of more than 150 g is going to cause death, and also a pressure of about 3.4 times 10 to the power 5 newtons per square meter is also going to lead to some skin damage as well as blood vessels and internal organs. Okay, so this is what is happening. So now the question here wants us to find the force, acceleration, and impact pressure, okay, for this 75 kg person who actually comes to rest in about 0.01 seconds and was initially traveling at 27 meters per second. Okay, so they want us to find the force, the pressure, as well as the acceleration, and then we compare these values to the threshold values that can cause some damage or death or bone fracture. Okay, so we're going to find the value of a given force and compare to the threshold, and then we can see whether or not this force is going to cause a bone fracture. We do the same for the acceleration. We find the acceleration in this case of this passenger. Okay, we find the rate at which he is accelerating, and then we compare that to the threshold of 150 g and see whether or not it's going to cause death. We also do the same for the pressure and see whether or not it's going to cause damage to the internal organs as well as the skin. Okay, so the data we know here is that okay, so these are the conditions here. Actually have them. So we are being told that if the force on this passenger is greater than 90 kilonewtons, we are going to have a bone fracture. If the acceleration is greater than 150 g, then we are going to have or record a death. If the pressure is greater than if the pressure is greater than the threshold, I think I meant to write threshold. Okay, if the pressure is greater than the threshold, I think I can just write that. Threshold, we're going to have damage. Okay, damage. Okay, like this. So if the pressure is greater than the threshold, we're going to have damage to some internal organs and the skin, okay, depending on the area, surface area upon which the pressure is acting. Okay, so now let's go and find the mass, the acceleration, the force, and the pressure. Okay, we know that the mass of this passenger is 75 kgs. He's traveling initially at a speed of 27 meters per second, and he stops, okay, decelerates rather, or within 0.01 seconds. Okay, and the area that we're given, and we're going to need this at some point, the surface area upon which the pressure is going to act is 0.5 meters, square meters. Okay, so let's find the force then. We know that the force equals change in momentum over the time. Okay, therefore change in momentum of this passenger, we know that the final velocity, because he is going to stop, therefore final momentum will be 0, and we are going to have 0 minus initial momentum. We are getting a negative, which is negative m times u, okay, divided by the time. and we are getting a force of negative 2.0 times 10 to the power 5 newtons. Okay, so we can see that the magnitude of this force, magnitude of 2.0 times 10 to the power 5 newtons is greater than 90 kilonewtons. Therefore, we are going to have a bone fracture, very broken actually, because the force is much greater. Okay, much greater. Okay, so we have concluded about the force. Let's see, what acceleration does the passenger travel at? Let's see, acceleration is v minus u over the time, the stopping time, and we know that v is 0, so we're simply going to remain with negative u, which is negative 27 over this. The deceleration is going to be negative 2,700 meters per square second. If we compare this to 150 g, we're going to discover that this acceleration, or rather the magnitude of this deceleration, is still much greater than 150 g. Therefore, we are recording a death, very dead. Okay, then the third one is the pressure. Let's see how much pressure the passenger is going to be experiencing in this collision. Pressure, we know that is force over the unit area, surface area, and the force was already found. Just check here the force. Okay, so this force here is the one we're bringing down, so it's going to be the force over the surface area, which is 0.5 square meters, and we're getting a pressure of minus 4.1 times 10 to the power 5 newtons. Okay, so also here, if we compare with that 3 point something, we discover that this pressure is actually greater than the threshold. Therefore, we have also damage to the internal organs. So when this passenger experiences this collision, one, we are going to have a lot of broken bones and also death, of course. I don't know which one comes first, but I think broken bones, and then you die. Anyway, it doesn't matter. Die, and then also the internals are damaged. Okay, so I think okay, so this is the end of our tutorial sheet. So make sure you go solve. There's that question 2. Okay, so just try and attempt that one. I want to see some reasoning there. Put some physics. Okay, don't just explain as if you are don't just explain. I want to see some physics there. Okay, so we shall be doing this, and then it's how we're going to be doing our tutorial, so that everyone can have access to these explanations. In case you're having trouble, I'm sure they can help. Okay, all right, so until next time, I'm sure that will be